Today we will discuss about local search part 2. As always, the source code that I will use for explaining the concept is available on GitHub here. Sorry. Okay, at this URL. And today we will mainly discuss about strategy that consists in enlarging the neighborhoods to make sure that it can escape from local minima. And we will exemplify all the concepts on the traveling salesman problem, a well-known problem. So let's first consider the traveling salesman problem. So if you don't know the problem, but I'm sure you know it, it's find a circuit, a Hamiltonian circuit that goes through every node here, and that minimizes the total length of the circuit, of the tour. And the question I would like to ask you and to think about is, do you think that we can improve the length of this tour just by swapping some edges, for instance? So I'll let you think a little bit about it. How would you change this circuit, this specific tour, to improve the total length of the circuit? One way to do it is like this. You can, for instance, break the edges here. So you would remove these two ones. And then you would instead connect after visiting that one, you would go there, right? But in that case, you need to flip the order of the visit of all this path. So you flip the order. And then, of course, you need to reconnect the two. So you will also break that one and you will reconnect it like this, okay? This is what we call a Euclidean TSP, traveling salesman problem, because the distance is equal to the Euclidean distance here on a two-dimensional space. In an Euclidean TSP, it's quite easy to realize that in any optimal solution, you cannot have crossing edges. Why is it the case? If it's not the case, simply by breaking here the crossing, you can always improve the length, right? If you can find any two edges that are crossing in the Euclidean TSP, you can do exactly the same kind of move. So removing the two edges that are crossing and reconnecting the subcircuits here, and you would improve the total length. So it's quite clear that in Euclidean TSP, you cannot have crossing edges. This move that we just did of removing two edges and reconnecting them is called the two-opt move, okay? Because it only involves two edges here. And of course, you need to reconsider the order of the visit of this path. I made a small animation here to show you, okay, this is random points that I have placed on a 100 by 100 square. And then I have simply decided to do a random circuit. And then I have applied the two-up moves like I did before until I cannot do it anymore, until I have no crossing edges anymore. Okay, this was my stopping criterion. And then I arrive in this solution, right? This is an intermediate solution. This is the final solution. And you can see that only with this very simple idea of the two-opt move, I can reach pretty good solution for the TSP. Okay, so it's very efficient and it's very good in practice, this simple idea. A theoretical question that you should always ask yourself is the two-up move a connected move or not? So if you remember from a previous video last week, we said that a move was connected if it was possible to reach any solution just by applying a sequence of such a move that we assume that could be connected, right? And so a solution to answer this question, I will assume that I have a representation of the solution. And the representation that I will assume is that I will represent a circuit as a permutation, right? So I visit 1, and then I visit 2, then 3, then 5, then 6, then 7, okay, like this, 1, 3, and so on. And then we should ask ourselves, what does it mean in this representation to apply the two-opt move, okay? So if, for instance, you would disconnect these two edges, right? You would disconnect them, and instead you would replace it by this, and then you need to switch the order of the edges like this, and then you reconnect it like that. What does it do, right? So you will break 3, 5. So clearly you will break something here. I will put it in red. You will break something here in the middle, right? And you will also disconnect after that 4 9. Okay, so you will also break something here. So what you do when you will reconnect this is that you will take this sub array like this and you will flip it, right? You will flip it completely. So instead you will have 4, 8, 7, 6, and then 5, right? So you can check that. So 1, 2, 3, and then 4, 8, 7. That was 6. Okay, the 6 is it. 6, 5, and then 9, and then you continue the 2 as it was before. So 9, 10, 11, 1, right? 9, 10, 11, 1. We didn't touch to that part of the tool, right? So applying a 2-opt move is exactly the same as taking a subarray in the middle of the array in our representation of a circuit, and then you just flip it completely, this subarray. Once you have this representation and you know what the 2-opt move is doing, it's quite easy to answer this very important question of the connected neighborhood of 2-opt moves, right? Because assume that this is your best solution that you would like to reach. Is it possible, starting from this solution, to get closer to that one? Actually, yes, it's quite easy to reach it. The only thing to do is that you need to flip it you need to apply to a move to make sure that you will come to that solution. So the first thing that you will need to do is first to put the number 3 here in the middle. So probably you will take this subarray, okay? You will take this subarray and then you flip it, right? And then you put 3 here in the middle. Okay, that one is done. Okay, the 3 is done. I assume it's done. So then you need to put 1, right, in the middle. So again, you will do the same as before. You will try to find the 1, and then you will flip it. And so you will progress in that direction. And you will always place one more position correctly in the tool. And so it's always possible by applying a sequence of 2-opt move, and it's quite easy to find which one you should apply every time to reach a possibly best solution here that we have represented here with a star. Okay, so clearly the 2-opt move is a connected move, which is a good news, right? It means that it's a move that would give you the guarantee that if you would find the right sequence of 2-opt move, you can always reach optimality of the TSP just by applying this move. Of course, it doesn't tell you what should be the sequence that you should apply, but at least from a theoretical point of view, you can reach it.